All right, can everyone hear me? Good. So thanks so much for having me. It's really a pleasure to be here. It's actually my first time at the Santa Cruz workshop, even though I was up the road at Stanford for many years. So wonderful to be here, and I'm very excited to tell you today about something that's very close to my heart, namely the question of which dark matter halos can form galaxies. So I want to start by going back to the beginning, to our discussion on the first day, where we talked about the 1984 work and so on. The basic fact that we're all dealing with is that galaxies form at the center of dark matter halos. So here you're looking at a cosmological zoom-in simulation in a cold dark matter cosmology. And this is a roughly Milky Way-sized dark matter halo, at the center of which we expect a roughly Milky Way-sized galaxy to form, right? Now, below the mass scale of the Milky Way, smaller halos generally host smaller galaxies. We know this very well, and we've measured it observationally, for example, using satellites around the Milky Way. But there's a fundamental prediction being made here by cold dark matter that there's an entire mass spectrum of halos below the mass scale of the dwarf galaxy that I just highlighted. So it's a very natural and very important question to ask. Which of these halos actually manage to form a galaxy at all? And in particular, what is the halo mass threshold for star formation? Now, to make this quantitative, here's a figure from Risa Wexler's review showing the stellar to halo mass ratio on the y-axis as a function of the halo mass on the x-axis. So first thing, you can see what I was saying, below the mass scale of the Milky Way, below a halo mass of 10 to the 12 solar masses, this ratio plummets. Star formation becomes very inefficient. And at the faint end, we lack both kind of observational and theoretical understanding of what the galaxy-halo connection actually is. But it's fundamentally important in order to test these cosmological predictions. Now, there are lots of interesting questions that are raised by looking into the faint end of the galaxy-halo connection. For example, how did the faintest galaxies in the universe form? What does the existence of dwarf galaxies reveal about the nature of dark matter? I'll touch on both of these things. But I want to focus on the third one, namely, do completely dark matter halos exist? Now, as I said, we generically expect these objects to exist in CDM, but we don't empirically know yet whether they exist or not. And this has all sorts of implications. For example, the abundances of dwarf galaxies, the reionization history of the universe, 21 centimeter cosmology. I mean, I could go on, right? We really need to understand the answer to this question. So I want to present to you a simple physical argument for what sets the halo mass threshold for galaxy formation, and I'll show you some new predictions for this mass scale. Here's a plot that I will come back to many times throughout. So what I'm showing here is the critical halo mass necessary for star formation as a function of redshift. And in the very simplest picture, and a surprisingly widely adopted picture in the literature, there are only two physical processes that matter here. And you should be able to tell that I'm skeptical of this picture. I'll show you a generalization of it soon. First physical process before reionization is the atomic hydrogen cooling threshold. Right? So by setting the virial temperature of a halo equal to the atomic hydrogen cooling threshold, roughly 10 to the 4 Kelvin, then we can derive a redshift-dependent critical halo mass. And then after reionization, once the IgM is heated, then the virial temperature of a halo needs to exceed roughly 2 times 10 to the 4 Kelvin, right, depending on the details of the reionization model, in order to hang on to gas and keep forming stars. Now, once we have a model for the critical halo mass, we can turn it into a corresponding prediction for what I'll call the galaxy occupation fraction, namely the fraction of halos that are able to form stars or form a galaxy, I'll use those interchangeably, as a function of the final halo mass. And the basic assumption here is that the fraction of halos that form stars is simply a convolution of this critical halo mass threshold with a distribution of halo growth histories. So let me show you such a distribution. This is analytically generated. It's a very simple model. I'll describe exactly what I did in a moment. Here I've generated halo growth histories analytically for halos with a mass of 2 times 10 to the 8 solar masses at a redshift of 1. And that leads to the galaxy occupation fraction shown by the solid line in the right-hand figure. So in this picture, the minimum halo mass for galaxy formation is somewhere between 10 to the 8 and 10 to the 9 solar masses, depending on when you define that final mass. All right, so now what have I done here in order to generate these halo growth histories? I've actually used a very old model, but it's a useful one for this purpose. So I used Risa's 2002 fit to the mass accretion histories of dark matter halos. And I do this for two reasons. First, I'll show you that this leads to an analytically tractable occupation fraction. There's an analytic prediction for the galaxy occupation fraction in this framework. It's also interpretable in terms of halo concentration. So at a fixed mass, the halos that form earlier and therefore reach above this critical mass threshold are the more concentrated ones. So there's a correlated prediction here for the star formation properties and the inner densities of these objects. Now, I'll show you later in the talk that all of these results replicate when I use full merger trees from cosmological simulations and so on, but it's nice to start with a simple picture to get intuition. This model, atomic hydrogen cooling plus reionization, underlies, as I said earlier, a surprisingly large number of predictions throughout the literature. So I'm showing one very well-known example here. This is from Benitez, Yambay, and Frank, 2020, where they lay out this basic logic for the critical mass threshold, propagate it to the halo occupation fraction, and many subsequent, particularly semi-analytic works, use this kind of model in order to make predictions for low redshift dwarf galaxy populations and other things. But by now, you should be skeptical too, right? There's other physics that regulates galaxy formation in small halos at high redshifts. We've known this for a very long time. For example, atomic hydrogen is not the only coolant in small halos. There's also molecular hydrogen. Here I chose a plot from 2006 just to illustrate it because it contrasts these two processes nicely, but I could have shown the 1984 plot here equally. So molecular hydrogen is able to cool at lower temperatures than atomic hydrogen. It's more difficult to model because it can be dissociated by local radiation. I'll come to this in more detail. So that's one important effect, and there's actually another one, which is the relative streaming motion between dark matter and baryons. That's a cosmological effect, so there's a relative motion between dark matter and baryons that's imprinted at recombination. And that also raises the minimum halo mass for cooling. Surprisingly, neither of these effects has been incorporated in predictions for the galaxy formation threshold at redshift 0, at least in the kinds of semi-analytic models that I'm showing you here. Of course, some hydrodynamic simulations include such effects, but they generally don't have the resolution and dynamic range needed to make these predictions at redshift 0 for dwarf galaxies. So there's a few recent semi-analytic works that are really quite detailed that tackle this problem. So this work that I'm highlighting here from Nadler et al. 2023 includes really a long laundry list of effects. Lyman alpha, molecular hydrogen metal line cooling, photodissociation, molecular hydrogen self-shielding, and so on. And it propagates all of these into a semi-analytic model for the critical mass threshold. So these three solid lines, red, black, and purple, show the prediction for the halo mass threshold as a function of redshift, including all of these effects, and using the latest fits to the reionization history from Faucher-Giguère, and also using recent fits to the Lyman-Werner radiation field. So let's put these effects into the model, right? We all know they should be there, right? So let's put them in and see what happens. So here, I've added both molecular hydrogen cooling and the dark matter baryon streaming velocity to this critical mass threshold. And let's do the same exercise as before. So I'm convolving these with the distribution of halo growth histories. And now you can see that the story starts to change. So these blue lines compared to the orange lines are able to form galaxies in about halos that are about one order of magnitude smaller than before. So now the prediction for the minimum halo mass at redshift 0 is somewhere between 10 to the 7 and 10 to the 7.5 solar masses due to this efficient molecular hydrogen cooling. Interestingly, the fact that these blue lines hit 0 at particular mass scales is really dictated by the dark matter baryon streaming effect. You'll notice that this critical halo mass curve flattens out at high redshift. That's a signature of the dark matter baryon streaming. And that's really what pins down the relation here, whereas the molecular hydrogen cooling is what's pulling the blue lines to the left relative to the orange lines. Okay, so I mentioned earlier that we get some analytic tractability from this particular model. I just want to sketch this for you. I'm not going to go into too much detail. But let's consider a very simple case where a halo just has to exceed a certain mass at a certain redshift in order to form stars. Then the occupation fraction is simply the probability that it exceeds that mass conditioned on whatever its final mass is. Okay, we can integrate that over a distribution of halo mass histories. It's not that complicated, and we get something that looks like an error function. Now, interestingly, there are three implications here. So first of all, the cutoff scale in the occupation fraction is essentially set by the mean concentration of halos evaluated at the final redshift. The slope of the occupation fraction is set by the scatter in the mass concentration relation. And this error function form actually fits to hydrodynamic simulations. So I'm showing one example here where this gray line was from my earlier work. That fitting function was motivated from hydro simulations. I think that's quite interesting. It's suggesting that all of the complicated physics that's going on in hydro simulations might essentially boil down to this kind of convolution argument. Okay, so let's get closer to observations. I'm going to consider the Milky Way satellite galaxy population. It's a wonderful tool to study this problem with because we have a whole spectrum of dwarfs within the Milky Way, ranging from the LMC, which is still actively forming stars, all the way down to the ultrafaints like Pictoris 1, which have extremely low stellar to halo mass ratios. To do this, I'm going to use merger trees from a cosmological zoom-in simulation. This is a dark matter-only simulation from the Milky Way suite. This was really wonderful work led by an undergrad at Stanford, also in collaboration with Risa and Yaoyuan Mao. And what I've done here is take one of these Milky Way hosts and resimulate it with very high resolution, so 6,300 solar mass dark matter particles, and also critically very fine time sampling and time resolution, particularly at high redshifts. Now, this turns out to be a pretty expensive simulation because these Milky Way hosts include realistic analogs of the Large Magellanic Cloud system and also realistic analogs of the Gaia Sausage and Enceladus merger, so their Lagrangian volumes can get quite big. All right, so back to the galaxy formation threshold. Here are the two critical mass predictions in orange and blue. And now let's convolve these with the actual halo growth histories from the cosmological simulation. So there's a lot going on here. The first thing you'll notice is that the shape of these growth histories are different than what we were looking at before. There's a few reasons for that. First of all, the subhalos at a certain point fall into the Milky Way and start losing mass. That happens at around redshift 1. Second thing you might notice is that the amount of scatter in these growth histories is larger than what we were looking at in the analytic model. And that's essentially a result of the cosmological environment. There's a greater diversity of ways to form a halo in this kind of environment. So on the right-hand side, we have the occupation fraction. Again, the blue case is pulled to lower masses relative to the orange one. But once again, this halo mass threshold comes in at about 10 to the 7. Now I'm working with the peak mass of the dark matter subhalo. So Milky Way subhalos with peak masses down to about 10 to the 7 M-Sun can form stars through molecular hydrogen cooling. And once again, lower mass halos don't form stars primarily because of the dark matter baryon streaming motion. In this particular prediction, what I did was I fixed the amplitude of the dark matter baryon streaming to its cosmic average. It's not a crazy thing to do. It could wiggle up and down a little bit depending on the large-scale environment we find ourselves in. Now there's one more intriguing thing in this figure, and that's the gray region. So this gray region is a posterior on the galaxy occupation fraction that I derived from an analysis of the Milky Way satellite population in 2020. Essentially, by forward modeling the luminosity function of Milky Way satellites, we can infer what their halo occupation fraction is. And you'll notice two things. First of all, this orange model is ruled out by the data. So that's telling us that at least some Milky Way satellites form stars through processes other than atomic hydrogen cooling. The other thing you'll notice is the blue line, well, it's kind of barely consistent. At the 2 sigma level, it actually is consistent. But it's a bit uncomfortable, right? We would like to actually populate halos more efficiently in this mass range. How might we be able to do that? So I think there's some interesting hints from recent high redshift hydro simulations. I'm going to show you one example here from Mike Norman's group at UCSC. In this ENSO simulation, what they did was at redshift 12, analyze halos and in particular break them down in terms of how they formed their stars. So the different colors here show you the mechanism by which a halo forms stars. So blue is molecular hydrogen cooling. That's the bulk of the halos. There are also some metal line cooling halos. But the shocking thing in this plot is that there are no atomic hydrogen cooling halos. So I thought that was a mistake when I first saw the plot, but it's actually 0. There are none that form stars through atomic hydrogen cooling, even though many of those halos are well above the atomic hydrogen cooling threshold. Okay? So what's going on? if you look into the gas distribution in this kind of simulation, what you see is the accretion onto halos is really filamentary. The gas is not virialized. In fact, none of it's really heating up even close to 10 to the 4 Kelvin. So this is classic cold mode accretion happening at very low halo masses. And unfortunately, this kind of effect, this lack of virialization, is not included in any semi-analytic model at these mass scales. Okay, so why is this also exciting? I think we will make progress in actually measuring this galaxy formation cutoff in the coming years. So we're poised to discover lots of new Milky Way satellites. We have a new forecast paper from the DESC collaboration that shows the LSST 10-year survey should be able to find basically all of the remaining Milky Way satellites in the southern hemisphere. That's very exciting. And in a forecasting paper that I led last year, what we showed is that factoring in all of those new detections, we can actually start to gain a measurement rather than just a constraint on this minimum halo mass. Here it's quantified as the mass scale of the cutoff in the galaxy occupation fraction. The thing that is particularly helpful for that kind of measurement is combining different satellite populations. So if you combine, for example, the Milky Way satellite population with M31 satellites, you break degeneracies in the modeling and improve the detection quite a bit. All right, so I want to end coming back to the cosmology to show you a very preliminary result. How does this depend on the nature of dark matter? Here what I've done is a similar experiment where I took a host halo from the cosmic simulation suite, which spans many non-cold dark matter models. So here you're looking at a 3 keV warm dark matter model. And I've asked the same question: which halos grow above the critical mass threshold at which time? Now, as we change the particle mass of the dark matter, so I'll go from 3 keV to 6.5 keV, two things happen. First of all, more halos are added because this is a colder model, but also the growth histories shift to earlier times. So we start adding more and more halos that reach above these critical mass thresholds, and finally, by the time we get to 10 keV, we start to form some molecular hydrogen cooling galaxies. So this is very interesting. It's suggesting that the current kind of constraints on warm dark matter just from counting Milky Way satellites can be substantially improved by factoring in the early growth histories of those systems. Okay, so I'll come to the conclusions. Hopefully I convinced you that the critical mass threshold for galaxy formation is close to 10 to the 7 solar masses. I think it's a really exciting time to study this both observationally and on the theory end. So happy to take questions. Thanks.
I have a question myself. So there's a new category of interesting objects called dark relics, which are allegedly just dark matter halos carrying a blob of gas without forming stars. And the gas mass, some of them, like observational candidates, can amount up to 10 to the 6 solar masses. So really quite comparable to your floor mass here, considering all the effects. Could you comment on that?
Yeah, I think it's really a question of the scatter, particularly the downscatter and the stellar mass halo mass relation. So you see that this occupation fraction starts to bend down even at a halo mass of 10 to the 9. So you can have objects that are actually pretty massive, have downscattered massively and not been able to form stars, but maybe have been able to hang on to their gas.
And what would be the physical cause of the downscattering?
The distribution of the growth histories. Yeah, yeah.
Okay.
A comment. So after ionization, the temperature got raised to 10 to 4 or a little over. The G scale is at least a few times 10 to 9. So if you equate T0 to Ti gene, there might be an underestimate of the threshold.
Yeah, I agree. So this is, yeah, I think they work out to be pretty similar, the critical halo mass you get from those two scales, but also it's in some of the models. I will check.
Very interesting, but shouldn't you lose most of the molecular cooling halos by tidal disruption? Because they form very early, they will be concentrated close to the center of the halo. So they should be more affected by tides than the average.
Well, I think this is an open question, and it goes back to what we were discussing earlier about the disruptability of satellites, right? Yeah. If we believe that the CDM halos are actually more resilient, then some of those galaxies may survive, but it's an open question.
Thanks, Ethan. That's a great, really cool model. I'm wondering if, sorry if this is naive, but I'm wondering if you're able to test how the minimum halo mass trend would evolve if you consider really low mass halos at early times that could have enriched gas falling into them, and then they're open to other forms of cooling.
Yep. So this is actually in the Nebrin model. I didn't go into it in too much detail. What they find in that particular model is it's only a small fraction of the mini halos that are metal enriched. But I think obviously there's uncertainties there, so we should talk about it.
Colleague.
Thanks for the great talk, Ethan. I'm curious if you could comment on the different shapes that your models predict compared to the Milky Way satellite census. It seems like there's kind of a steeper occupation fraction with respect to mass. Is that because there's like a different assumption about how long reionization lasts or something like that? It just seems like the 2020 results are kind of sharper than the newer models.
Yeah, so from the 2020 modeling, really all we have is an upper limit on M50 or on the scale of this cutoff. The shape of the occupation fraction is not well constrained. All I'm showing here is the best fit. But within this posterior, you can get shapes that are much shallower. So I wouldn't read too much into the difference in shape here.
Thanks.
Right. I suggest we move on. And let's thank Ethan again.